Hello, today we're going to look at chapter 14.4, specific heat capacity. Now you've seen this topic before at GCSE, so there shouldn't be anything too new. However, you do need to know the definition, so let's start with that. So it's the energy required per unit mass, so that's per kilogram, so per unit mass, to change the temperature by 1 Kelvin, although you can say 1 degree C because the interval between 1 Kelvin and 1 degree C is exactly the same. And the units are joules per kilogram per Kelvin. So here is the equation. Energy equals mass times specific heat capacity times the temperature change. Now I've written mc delta T, just here, but in some of your books it does use delta theta. So either way, theta is the same as temperature, and as I've already said, temperature can be in degrees C or Kelvin, but the triangle there means the change in, and that's the key thing. So let's just look at an example. So apple crumble, when it's been in the oven for, 25 minutes, it comes out at 200 degrees, the same temperature as the oven, because it's heated up. But when you put it in your mouth, either the apple or the crumble, one of them is going to burn you. And I think we all know that it's the crumble that does not burn you, it's the apple that does burn you. And it's because apple has a higher specific heat capacity than the crumble. Apple contains more water than the crumble, and water has quite a high specific heat capacity of around 4,200 joules per kilogram per Kelvin. So a high specific heat capacity, what that means is it takes longer to heat up, but it also takes longer to cool down, and that's why we use it in central heating around the house. It might take a little while to heat up, but once it's hot, it will stay at a nice temperature for quite a long time. Something with a low specific heat capacity, that will heat up quicker, but it will also cool down quicker. So oil will have a lower specific heat capacity, it heats up really quick, but it also cools down quick as well. Now if you want to measure the specific heat capacity of an object, there is a practical to do, and it is a PAG that you'll do in lessons. So I won't spend too long on this because you'll do the practical for yourself. But let's just go through the basics of it. So first of all, let's just look at the circuit diagram. So it's got an ammeter on there, so that always has to go in series. And there's a voltmeter around the heater, which of course goes in parallel. So the heater is the immersion heater that goes inside the block, probably an aluminium block, although it doesn't need to be, it could equally be water or any other material. So each material will have its own specific heat capacity, and that's then unique to the material. So the equation E equals mc delta T, but energy or work done or energy transferred is also equal to VIT, because energy equals power times time and power equals current times potential difference. So VIT equals mc delta T, and if we just think about what the constants are, well, the potential difference in the current won't change, the mass of the object won't change, and the specific heat capacity won't change either. So that leaves little t for time and big T for temperature as our variables. So let's rearrange the equation in the form of y equals mx plus c, although in this case there's no plus c. So we'll start with the equation VIT equals mc delta T. So we'll put temperature on the y-axis, mainly because we always tend to put time on the x-axis. So we need to remember our y equals mx and then plus c, but there's no plus c, so we can just ignore it. So I rearrange for delta t equals VIT divided by mc. And then I've just put a delta sign in front of the time because that's what's going to be varying as well. So delta t equals Vi over mc times delta little t. So I just rearranged it to make it look nicer so I can compare it to y equals mx plus c. On the y-axis is delta big T, on the x-axis delta little t, so our gradient by comparison is Vi over mc. We want to find the specific heat capacity C, so that's then Vi over m times our gradient. So in other words, we need to get some data, plot a graph, find the gradient, whack it into the equation, and then find the value for specific heat capacity. So first things first, we get our data, we get a graph like this, and we need to find the gradient. So we do the change in the y-axis divided by change in the x-axis. So we've gone from 50 and 20, so y is 30, and it's taken 40 seconds. So our value for the gradient equals 30 over 40, which is 0.75. So that's our value for that. Now I'm going to make up some numbers here. So the current might be, 4 amps. The potential difference might be 10. The mass of the block tends to be 1 kilogram, but that doesn't always hold true. And then our gradient is 0.75. So that's then 40 divided by 0.75, which then gives a value of about 53 joules per kilogram per Kelvin. This would be a low value for specific heat capacity, so it's something that heats up quickly, but it also would cool down quickly. And actually, it has heated up really quickly. It's gone up 30 degrees and it's only taken 40 seconds to do it. And then to finish off, if you can have a go at the summary questions, please, and then make sure you mark it. And any queries or questions, please get back to me.